Helium shortage and supply chain disruptions. Implications for science and technology amid the Iran-US conflict. The global helium market has entered a period of severe instability following escalating tensions and military conflict involving Iran and the United States in the Persian Gulf region. Damage to Qatar's Ras Laffan industrial city, one of the world's largest helium production and liquefaction hubs, and disruptions to shipping through the Strait of Hormuz have significantly constrained global helium supply. Because Qatar normally contributes nearly one-third of worldwide helium production, the conflict rapidly transformed an oversupplied market into a supply-constrained one, leading to price increases, logistical surcharges, and regional shortages across scientific and industrial sectors. Helium is a strategically critical raw material due to its unique physical properties, including extremely low boiling point, -268.9 degrees Celsius, chemical inertness, high thermal conductivity, and nonflammability. Unlike many industrial gases, helium cannot be synthesized economically and is obtained primarily as a byproduct of natural gas extraction. Commercially viable helium reserves are geographically concentrated mainly in the United States, Qatar, Algeria, and Russia, making the supply chain highly vulnerable to geopolitical instability and transportation disruptions. The recent conflict highlighted the fragility of this supply network. Military attacks and maritime restrictions around the Strait of Hormuz disrupted exports of liquid helium stored in cryogenic ISO containers, while many shipping routes became inaccessible or prohibitively expensive. Market analysts reported that helium spot prices doubled within weeks, reaching nearly $190,000 per metric ton, while logistics surcharges increased by as much as 30%. Semiconductor manufacturers in East Asia, especially Taiwan and South Korea, responded by securing premium-priced helium inventories from North American suppliers, intensifying global competition for limited supplies. Scientific research infrastructure has been particularly affected because helium is indispensable for cryogenic cooling applications. Nuclear magnetic resonance, (NMR), spectroscopy, superconducting quantum interference devices, SQUIDs, particle physics instrumentation, and magnetic resonance imaging, MRI systems all rely on liquid helium to maintain superconducting magnets at temperatures near absolute zero. Modern NMR spectrometers typically contain 90 to 120 liters of liquid helium, and warming these systems due to insufficient coolant can damage superconducting magnets and require costly recommissioning procedures. In some cases, restarting an instrument may consume helium worth tens of thousands of dollars. Research laboratories across Europe and North America have reported delayed deliveries, reduced allocations, and the need to order helium months in advance. Institutions dependent on Qatari supply chains, particularly those supplied through major industrial gas companies such as Air Liquide, experienced heightened uncertainty. Consequently, laboratories have increasingly adopted helium conservation strategies, including recovery and reliquefaction systems, optimized cryostat designs, and scheduled refilling protocols. Beyond scientific instrumentation, helium shortages are exerting major pressure on semiconductor manufacturing and advanced electronics production. Helium is essential in extreme ultraviolet, EUV, lithography, leak detection, wafer cooling, plasma processing, and inert atmosphere generation during chip fabrication. Advanced semiconductor nodes used for artificial intelligence, AI accelerators, and high-performance computing devices require particularly high helium consumption. Manufacturers such as Taiwan Semiconductor Manufacturing Company and major South Korean chip producers reportedly increased strategic stockpiling efforts to maintain uninterrupted production. The crisis, therefore, exposed helium as a hidden but critical dependency within the global AI and semiconductor supply chain. Analytical laboratories have also faced operational disruptions. Gas chromatography, GC, and some mass spectrometry techniques use helium as an inert carrier gas because of its favorable diffusivity and chemical stability. Reduced helium cylinder availability forced many laboratories to transition toward hydrogen or nitrogen carrier gases. Although technically feasible, these substitutions often require extensive instrument recalibration, safety modifications, and redevelopment of analytical methods. The helium shortage further underscores broader concerns regarding critical material security and geopolitical supply risk. Studies applying the geopolitical supply risk, Geopol risk framework, have classified helium as a high-risk critical resource because production is concentrated among a small number of exporting countries and because transportation infrastructure is highly specialized. Major importing economies, including China, Japan, South Korea, Germany, and Canada, remain vulnerable to supply interruptions arising from geopolitical conflict, maintenance shutdowns, or export restrictions. Historically, helium has repeatedly experienced supply crises. The United States dominated global helium production throughout much of the 20th century after establishing the Federal Helium Reserve under the Helium Conservation Act of 1925. However, privatization and gradual depletion of federal reserves, combined with rising global demand from healthcare, aerospace, fiber optics, quantum technologies, and semiconductor manufacturing, have increased market volatility over the last 2 decades. The current disruption has accelerated interest in long-term mitigation strategies. These include expansion of helium recycling technologies, diversification of supply sources, development of new extraction facilities in North America and Africa, and greater substitution of helium in non-critical applications. Nevertheless, for many cryogenic and semiconductor processes, no economically viable large-scale substitute currently exists. As a result, helium remains an essential yet geopolitically vulnerable resource underpinning modern science, healthcare, and advanced technology industries.